All right, so in this session, we're going to be talking about exotic physics with the ngEHT. We've got 5 speakers, which means that each presenter will get 10 minutes for presentation, followed by 2 minutes of discussion. Our first speaker is Yifan Chen. Are you able to share your screen?
Yes, sure. Okay, can you see my screen?
Yes, looks good.
Okay.
So go ahead and take it away.
Can I go now? Okay.
Go ahead.
Okay, thank you. So I would like to thank first the organizer to give me the opportunity to talk about work looking for axiom using EHT and next generation EHT. Since I already gave talk in February, so I will most focus on the more recent part where we update using this year's EHT data to constrain axioms and some work for the future ngEHT. So I have many collaborators. I think in this conference, Chen, Long, Lu, Sen, Yusuke, and Xiao are here. So let me start. So axion is a kind of pseudo particle, a hypothetical particle, which is a pseudo scalar, and it has very strong motivation in the particle physics. It can solve the so-called strong CP problem, and it is generally predicted in the theory with extra dimension, like string theory. And it's also the perfect dark matter candidate. So when the max of the axiom is at a certain order, like in the same order as the gravitational radius of the black hole, it can take energy from the rotation energy of the black hole and get energy through the superradiance and form a bounded state, which is so-called a gravitational atom. And this bounded state carries as a wave function very similar to the hadron atom cases. It has a radial part of a wave function, and it has the polar angle sin theta. And it also has a time oscillation part of omega t, and this phi angle is in the black hole coordinates the azimuthal angle since it carries angular momentum. And the maximum density of this gravitational atom can saturate the decay constant. And the oscillation frequency is nearly the mass of axioms. And in the presence of axion photon couplings, it can mediate the so-called Beer-Fringes effect, which means the left and the right circular polarized photon have different the dispersion relations. Finally, the electric vector position angle, which is defined as the angle of the linear polarization Q and U, are shifted by the axioms. So more precisely, you can put axion photon coupling into the radiative transfer equation in terms of linearly polarization Q and U. And this is the differential equation in terms of S is a Feynman parameter, and you have emissions, and this axiom term will appear in parallel with Faraday rotation. However, this term is frequency independent compared to the for the photons compared to the Faraday rotations, and it's proportional to the gradient of the axiom along the line of sight, which means if you integrate out along the line of sight, then for each photon, it's a totally topological effect, which makes this shift of the axiom, the EVPA to proportional to the emission, the axiom field value at the emission point, this X mu emission. So this is this example. These green lines are the position angle of the from the relation, and this is the EVPA pattern. And if you look at the sky plane along this azimuthal angles, then you will find this shift of this EVPA is like a propagating wave. This is due to this in the black hole coordinate, axiom carries angular momentum. And if you project out to the sky plane, it goes like the propagating wave. So this phi in the BL coordinate becomes this ver phi on the sky plane, and it oscillates. Then you can fit this the oscillation of this line with the amplitude and the relative phase. So that's the EVPA shift and the amplitude and the relative phase. So the benchmark we take is the suborbital reef with vertical magnetic field around M87 stars, and it can from this their paper the model. And we scan the axiom mass in a certain mass windows, which correspond to oscillation period between 5 and 20 days. So here is one example. We are using the color of rainbow to show the variation of EVPAs in time. So from red to purples, you can see this vary. And this is the fit of this amplitude and the relative phase. So these are relative phase and amplitude. So first, if you look at the relative phase, it gives you a very nice cosine. This is due to the emission point. Since for each point, the EVPA shift is related to the axion field value at the emission. Then the T emit is different for at different pixels, or as you see. And for example, if you have 17 inclination angles, then the emission time at here and here are different. So then it gives you a cosine function in terms of this verify. This is due to the this time delay from this to this. And you also see from under amplitude, there's asymmetry along this verify. And here is highly suppressed. Here is in the region that most dense, most photon come from, and most lensed photon come from. And the lensed photon carries a different phase, delta 1, 2. And this delta 1, 2 is related to the time delay and the azimuthal shift between the lensed photon and the direct emission. So this lensed photon behave like some washout effect. Then you sum up these two emissions on the single pixels, and which give you the suppressing of the EVPA here. So, this is the work we are using this year's the data of the EHT to constrain the axion photon couplings. Since they publish only 4 days of data and only 2 days on this azimuthal EVPA, the quantity we define is the difference between 2 sequential days. So 1 day interval, and which give you a suppressing factor when the axion oscillating period is much longer than 1 day. Then the uncertainty of this azimuthal EVPA is used for us to constrain this axion photon coupling, the G phi gamma times the axion decay constant phi. You can see in this plot, these are the previous astrophysical constraint. And if you use this year's EHT data, you can already constrain to much better than the previous astrophysical constraint. So the dark green and the light green are depending on different spin of the M87 stars, which we don't know yet. And the different spin will correspond to different axion superradiance window. And this constraint becomes weaker at lower mass because the wave function is suppressed, also because we define the observable as a difference between 2 days. So the longer the oscillation period is, the highly suppressed the signals. So for the future is we also, as we know, for the in the most far away future, we will have the telescope into the space and Lagrange 2 point, and we can resolve a lot of horizon skew black holes. So what we did is we try to scan different parameters of the black holes as well as accretion flows. So these are different spin of the black holes with the face on to edge on. And these are different magnetic field as well as the velocity distribution of the analytic reef models. So which will give you the different axial mass window between this 10 to minus 22 to 10 to minus 17 EV. So in the previous case, since we only have M87 star, so the axial mass window is very narrow here. So as I just mentioned, the dominant lensed photon comes from this the dominant washout comes from lensed photon. So once you remove them out, all these cases give you very universal predictions. So which means probably the best observable to look for axion is not the photon ring, it's the photon a little bit far away from here. So where the lensed photon doesn't contribute. Or if the spatial resolution is high enough, we can remove them. So that's our prospect for the ngEHT is once we can have much better spatial resolution, we can correlate the EVPA shift at a different radius without this lensed photon contribution, also at different frequency, which probably in the near future we can already do. For example, at 86 gigahertz, the washout from this lensed photon becomes suppressed due to high optical thickness. So this green line is the 86 simulation we did. As you can see, here is less suppressed compared to the red and blue line, which are the 230 and 345 gigahertz. Also, if we are looking at this observable at 10 gravitational radius, these are not suppressed at all. So they are much better observable compared to this intensity weighted azimuthal EVPAs. Also, we expect longer and sequential observations because in such case, we can also do the Fourier transform to both angular mode verify as well as the T. Then verify and T, then we can define this the shift of the EVPA in terms of this different angular mode. And the dominant at face-on case is, of course, n equal 1, since it's like a propagation wave. At a higher inclination angle, there will other modes appear. So we also expect better resolution for EVPA and a better understanding of accretion field and jet. So another important thing is if we can understand the intrinsic variations of EVPA, then we can model it as a kind of noise. So which we hope some future GMHD can tell us how the astrophysical accretion flow can vary. Okay, that's all. Thank you very much.
Thank you. So now we'll take questions. As I wrote in the chat, feel free to either raise your hand or type it in the chat, or also on Slack, for which we have a specific channel. First question comes from Marshall. I see you've just written it. If you want, you can unmute yourself.
So yeah, I was just wondering which sources would optimize this process. Would you want to have bigger sources, smaller sources, faster rotating sources, binaries? What would be the best sort of source to look at?
The best sources, I think, is optically thick and geometric thin disk.
Like optically thick at the radio frequencies you're looking at.
I think we are not dependent on frequency. So as far as there's no like washout effect, everything is the same since it's frequency independent. So yeah, no frequency dependence. For thin disk, for Novikov solvent disk without lensed photon, everything are very universal, just as what I show here.
Richard, why don't you go next?
Yeah, so of course, these astrophysical plasmas can be very messy and degenerate. And another constraint to add to the mix would be positrons, which are known to be produced in AGN like M87, and which a lot of these models are doing. And positron effects on electric vector polarization angles may add a systematic where even changing by a few percent, you'd actually see large rotations of electric vector polarization angles depending on the thickness, the Faraday properties of a lot of these plasmas. So that's just another thing that would be good to consider.
We haven't considered yet. So what's the difference between positron effect and the Faraday rotation?
Oh, it's just that they're far greater when there's a large propensity for Faraday thickness of a material. So in some materials, the positrons don't necessarily affect the electric vector polarization angle, but in others, especially the Faraday thick ones, they do.
We haven't considered that, but I think that's probably more interesting for the neutron star or magnetar, since they can produce the Franck-Schwinger effect strongly.
And some AGN.
Some AGN. Okay, that we haven't considered.
Thank you.
So Alexander has said that he has some technical problems. Is Susmita Jana here? Or Włodzimierz Piechocki, sorry for butchering that name, I'm sure. Or if not, Parth, are you here on the call? Perhaps they were all anticipating going later. Alexander, how are your technical difficulties? Right. Yeah. In the meantime, let's get in a question from Ziri Yunsi.
Thanks a lot, Angelo. Thank you, Yifan, for a wonderful talk. Really nice to see sort of novel approaches to constraining fundamental fields. It's more sort of a comment / question, following on a little bit in a similar vein to Richard's. So you say that it's good to go for optically thick, and one of the things it's a comment, but I also wonder what your take on it is. That these are magnetoactive plasmas, and all of these radiative transfer calculations that we use in the EHT thus far, and everywhere in the world as far as I'm aware of, they're in the geometric optics limit, and they. So what does that mean? Principally, it means that we don't worry about the the refractive index or the dispersive properties of the plasma, but in particular how that's a frequency dependent thing, which can lead to a shift away from geodesic motion, depending on the frequency of interest of a particular photon. And I wonder, can you, it's not something you could do off the top of your head, but that isn't something we actually account for. It is something which is important, since now you're referring to this regime, and how strong is a magnetoactive effect like this. So there are a lot of works by, so I know Avery Broderick did some work in his PhD days on this. There are works by people like Don Melrose, who've looked into the theoretical formulations of this, but how strong is this particular effect, which you say is frequency independent and beneficial at high optical depths compared to the effect that I mentioned? Because I would think that actually you'd want somewhere that's in between optically thick and optically thin.
Yes, I now I understand what you mean. So what I mean, frequency independent is purely for axions. However, for some like other astrophysical effects, they are all like frequency dependent. So I think if you correlate different frequency, you can remove some of the astrophysical uncertainty, like the Faraday rotation, also probably the positron effect that Richard mentioned. Yeah, I hope so. So, but I'm not an expert in this plasma. Maybe I can discuss also with Yusuke about these points that you mentioned. Then for the optical thickness, what I mean is purely because there's no like the photon all come from one sphere, which are nice predicted for the emission point. Because if the emission point is not clear, then we don't understand how the signal should behave as. If they are totally a geometric thin disk and totally optical thick, they all come from the equatorial plane. That's the most dense region for the axion field value. So that's what I mean for that.
Okay, great, thank you.
Okay, thank you.
Marshall, did you have another question, or is that an old hand? Okay, so again, if Susmita,
Can I raise a point here?
Go ahead.
I mean, are we just waiting for people to show up, basically?
Yes.
Can I raise a point then that was raised yesterday and I was sort of curious about? Has anybody looked at sort of like what limits you could set from the brightness or background of the black hole event horizon itself, in the sense of very redshifted high frequency stuff that's been redshifted down into the radio? And what I mean by stuff here is like, I mean, if you look at the Hawking radiation, the Hawking radiation actually comes from outside of the event horizon. In fact, it comes from up to 80 times the short scale radius of the event horizon. So you might imagine that something was going on at like say you're creating protons, say, just to pick something. Protons would be redshifted down into 200 gigahertz or so for a black hole of about 1,000 solar masses. You could just figure, just say, well, I'm broadcasting a gamma ray at that frequency. What's its redshift? You can just calculate that, and that's what you need is about 1,000 solar masses. Has anybody ever worked through that and tried to estimate, what kind of bounds the NHT or ngEHT could set just by saying the black hole, shadow, the black hole shadow itself is the event horizon itself is dark at this level, and therefore that sets this level, and what emissions might be coming from it at these higher frequencies or higher energies?
I'm aware of very recent work led by Andrew Chale trying to characterize what he defines as the inner shadow. How dark is the dark patch of rays that land on the event horizon, if that is the spirit of your question.
That sounds similar. How do you, Andrew Chale, you said?
That's right. So C-H-A-E-L.
Okay, C-H-A-E-L.
Yes, and yeah, this comes from ordinary GRMHT simulations, and yeah, it is useful to characterize how dark that is to rule out things like a boson star, for example, for the specific calculations you've suggested. I'm not aware of any other work. Anyone else can jump in if you know more.
If I may, to take that discussion, it's an interesting question in the direction of like EHT and ngEHT instrumental requirements. For the EHT, we have a dynamic range of around 10 for the M87 image. So we can resolve that central brightness depression, which presumably Marshall, I think that's what you're referring to, which we think is coincident with the actual event horizon proper of the black hole. So one of the big things I think personally that would be good to push for with the ngEHT would be to go for higher dynamic range static images. And what that would enable us to do is to say, okay, if we can see it as a central brightness depression, which is 3 orders of magnitude dimmer than that surrounding presumed photon ring, then how many objects in that whole sort of, zoo of non-black hole horizonless objects could mimic that which a Kerr can produce without actually being a black hole, for instance, right?
Do you think that's technically feasible?
I'm not in a position to answer whether it's technically feasible because I'm not an engineer or an instrumentalist. However, it is something that is on the table for discussion this week. Actually, there's a session on Wednesday on the Lego exercise, which is designed for us to see.
I think that actually has 2 sides, of course. One is, can you do it? But also, like, if you could do it, what could you do with that? And I think that's something that would be very useful to write up, probably.
Right, I agree completely, and I'm coming much more from the angle of what can we do with that, and that is, okay, if you can see that central brightness depression is 3 orders of magnitude dimmer than everything else around it, like the accretion flow, the photon ring, and so on, then you're basically saying it's, that's a tight constraint on it being a black hole, right? It doesn't just give you a constraint on the fact it's a black hole. It also enables you to rule out, based on very simple image-based modeling arguments, all sorts of other black hole mimickers.
Yeah, because you would expect stuff to, interact with a non-black hole. Well, I mean, it's not event horizon, but whatever you want to call it, surface.
Yeah, so it could have
a star or something.
All right, let's move on to the second speaker who is ready.
Oh, good. Sorry.
At this rate, we may be able to return to this extended discussion. You can also continue in the chat or in Slack as well. Alexander, are you able to share your screen?
Hi, how are you? Let me share my screen. Okay. You can see?
Yes.
Okay. You can hear me? You can hear me?
We can hear you, yes.
Okay, thank you.
If you want to hit play, we can make sure we're looking at the right screen.
I need this only, okay. I need to do that. Okay.
All right, looks good.
Hi, everyone.
Take it away.
Thanks. My name is Alexander Bonilla. I am currently PhD candidate in physics at the Departamento de Física of the Universidade Federal of Juiz de Fora in Minas Gerais, Brazil. I'm going to present this work. It's namely light and ultralight spaces and supermassive black holes. And this work is in collaboration with Héctor Ortúa and Andrés Castillo. Okay, I'm going to begin. This is the outline. Introduction and motivation, theoretical framework, neutrinos and Z prime bosons, methodology, preliminary results. Introduction and motivations. Okay, the standard models is a very successful description of particle physics connecting the weak, strong, and electromagnetic force to the framework of the gauge symmetries. Only the later two are unbroken symmetries. For example, bring with them conserved quantum numbers, for instance, color and electric charge, respectively. The search for additional force has always driven particle physics, but has so far not been successful, resulting in tight bounds either on the strength or range of the new force. Baryon and lepton numbers are the only classical conserved quantities in standard models, taking in account that the lepton mixing pattern observed in neutrino oscillations proves the no conservation of individual lepton numbers. For example, for the three generations, electron, mu, and tau, or linear combinations thereof. Classical symmetries of the Lagrangian can be broken at quantum level through the triangle anomalies, which have to be cancelled in order to obtain a valid quantum field theory. On the other hand, cosmological and astrophysical data sets can be used to set limits on these new species that may emerge and that complement the work done in particle physics, for example, accelerator, reactor, atmospheric, for example. Okay, theoretical framework. I'm going to speak about the neutrinos and zeta bosons, but we are working, for example, with actions and other like and ultralight species. This work, for this work, we are concentrated, we are focusing the BL symmetry, baryon lepton symmetry, where the anomalies can be cancelled simply by introducing three standard model singlet right-hander neutrinos, which automatically lead to massive active Dirac neutrinos in this case. You know that, for example, in the standard model of particle physics, you don't have these three right-hander neutrinos, and it's possible to detect these three right-hander neutrinos is physics beyond the standard models. On the other hand, Dirac neutrinos aside, an unbroken U1BL symmetry brings with it only one more particle, the gauge boson, the gauge boson zeta prima, coupled to the BL current through this formula. And here, for example, G prime is the coupling constant, and zeta prime and G is the zeta prime boson, and the current in this case is no Scharger current. On the other hand, the particle content and the respective quantum numbers of the model is listed in the table 1. The presence of the three right-hander neutrinos, one per generation, cancel gravitational mixed Kirill anomalies of Booth's gauge symmetries. For example, you can, this is the model. When in the table 1, you have the shares assignment to the particle content of the minimal U1 symmetry or model symmetry. In this case, you can look that we have the three right-hander neutrinos, and on the other hand, you have the budget of elemental particles that we have into account, for example, in the very early universe. And we need to take into the account the grid of the freedoms that you can see in the down left side of the screen. I don't can see my mouse. Okay, no problem. And this is a very knowledge number, but for taking into account the zeta prime boson, we are introduce this degree of freedoms, for example, into the excess of the neutrino species. For example, we know that the relativistic species of the effective characterize the three generation of neutrinos, active neutrinos, for example, but this number in cosmology is very knowledge, it's 3.046. But when we do cosmological constraints, for example, in this case, this number can be different of this traditional number. In this case, this excess of the degree of freedoms can be due, for example, to the zeta prime bosons in G star, for example, and the three right-hander neutrinos is the parameter GAs in equation 2, and we can introduce this excess from the equation 3, for example, the Hubble rate. In this case, is only for radiation epoch, but we can extend this parameter to with the goal to introduce cosmological proofs. And for example, the equation 5 is a Friedman equations. And in equation 6, you can look that we have, for example, a dimensional density of radiation connected with the dimensional density of photons, for example, and the number 3.046 is the effective degree of freedoms of relativistic species of three active neutrinos, and delta NF is this sex due to presence of the three right-hander neutrinos and the zeta bosons, for example. And the useful formulas, useful equations are presented in the equation 7. For example, the horizon to the horizon scale to recombination and diameter angular distance to obtain constraints of these parameters. We use in principle different data sets. For example, we use cosmic microwave background, baryon acoustic oscillations, supernova type 1 that are traditional or classical cosmological proofs, but we have, for example, cosmic chronometers or galaxy clusters, Big Bang nucleosynthesis, and through this data set, we can put observational constraints. For example, how you can see in this plot at the to the left hand side of the screen. I can show you constraints on the H parameter or that represent the Hubble parameter today. up to date, and the omega matter or content of the matter of the universe that have been account baryons and dark matter, and have been account to massive neutrinos, for example, in this case. And we can see that we can obtain constraints in the mass of the zeta boson. That is our goal. And for example, in sigma 8 2. This is, for example, this is important for us to obtain constraints in Hubble parameter and sigma 8 parameter that is very, very well known in cosmology, that those two parameters are in tension in between cosmological proofs to low redshift and high redshift how cosmic microwave background. And the introduction of right-hander neutrinos and zeta boson can be allow us alleviate this tension, for example. By the other side, you can see in the right side of the screen the evolution of the three right-hander neutrinos in the excess of the relativity degree of freedoms, and it's possible in the near field obtain constraints. For example, in experiments how CMB stage 4 or Big Bang others experiments that are coming in the near future. And how preliminary result we can obtain constraints on the in the zeta bosons, but we are working to use, for example, we will use a data point of N87 and H2, for example, obtaining for diameter angular distance to put constraints on the zeta bosons. We need, for example, simulated data from the supermassive black hole population that can be detected for next generation Event Horizon telescope. We can use, for example, the information of primordial supermassive black hole produced by the phase transition to set limits. This information can be obtained, for example, from the PTAs, the pulsar timing arrays in nanohertz frequency for example, continuous gravitational waves. And we can explore baryogenesis and leptogenesis through various production mechanisms such as Hawking radiation. That's all. Thank you very much for the attention.
Thank you, Alexander. So now we have plenty of time for questions and further discussion. As far as I know, the remaining speakers of the session have not appeared. So first we have a question from Marshall. Go ahead.
Hi, thank you very much. Nice talk. I had the same question as I had before. Which black holes would maximize your scientific return? Do you want bigger ones or smaller ones, or what would be sort of your ideal observing object to observe?
Okay. For example, in this case, it's very interesting thinking in the primordial supermassive black holes that various research of the this excuse me. For example, you have, for example, mechanisms to produce a supermassive black holes in the early universe. The supermassive black holes have an initial mass of more or less 10 to 9 solar mass, but are produced to the size of the horizon as this early era, and are produced by, for example, phase transition. And these phase transitions have, for example, a signature that can be detected, for example, in programs called nanographs or International Pulsar Timing Arrays, or SCA, for example, can detect this signal, for example, produced by phase transition. Or in other case, you can complement information from the nanographs observatories with the LISA observatory, for example, to obtain information of individual supermassive or merger of supermassive black hole. More or less is the idea. I don't know if I.
Well, okay, but I didn't hear you say ngEHT there.
Okay, but yes. In this case, with the diameter angular distance obtaining for example, for the N87 star, we have only one point to do a cosmological constraint. But for example, if we can simulate data from the other supermassive black holes to different redshift, for example, I don't know, we can obtain more precisely constraints on these parameters, and we need this simulated data to put constraints to the future thinking to the future detection with next generation of supermassive black hole is one possibility. The other possibility is to obtain information of the mergers of massive supermassive black holes, or massive black holes is possible too. But in this case, the strategy is different. Why you need obtain information of the continuous detection, for example, but the strategy change a bit more.
Okay, we actually have an additional speaker here.
Thank you.
Vishva Patel.
Thank you for the question.
And this person was originally scheduled to speak on Thursday. Apologies that my schedule appears to be out of date. But Vishva, are you able to share your screen and turn on your mic?
Alexander might need to share his screen.
I have some problems here.
Yes, can you please stop sharing? Okay, there we go.
Okay.
Okay, we see your PowerPoint.
Okay.
We do not hear you, Vishva, however. Okay, I can now hear you, although you're quite quiet.
Hello everyone, I'm Vishva Patel, and first of all, thank you ngEHT for giving me this opportunity to present my work here.
We need to up her volume somehow. I can barely make out anything.
Vishva, is it possible for you to turn up your volume?
हाँ.
That is an improvement to me.
Oh, my voice. Okay. Am I audible now?
Okay, that's great. Thank you.
Okay. So today I'm going to discuss about orbital precision in general relativity, which is based on this article. So mainly I'm going to talk about two things: the orbital precision in black hole spacetime and naked singularity spacetime. And from that, from the orbital precision, how can we distinguish black holes and naked singularities? So there are several ways from that we can differentiate that. First of all, the shadow of the compact object. Second one is gravitational lensing. Third one is redshift of a photon passing through the collapsing cloud. Fourth one is accretion disk properties of the compact object. And the fifth one is the precision of a stars orbiting around the compact object. So here this left side image is the map of our Milky Way galaxy, in which we are located somewhere here with our solar system, and the center of our galaxy is located somewhere here with this Sagittarius arm. Now, as per the literature and observations, we can say that there is a presence of a compact object in every galaxy's center. So in this right video, this star symbol represents the compact object which is present in our center of galaxy. And there are many stars orbiting around this compact object. We called these stars as a S stars. So from this precision of these S stars, we are going to predict whether it's a black hole or a naked singularity. So first one I have taken here is the black hole spacetime, which is the Schwarzschild spacetime. Schwarzschild spacetime is the spherically symmetric vacuum and static solution of Einstein's field equation. Here in this orbit plot, this brown circle shows the perihelion approach of a star near the central object. Here this red orbit is for the star's orbit in the Schwarzschild spacetime. Here this arrows shows the motion of the star, and this black arrow shows the precision of the orbit. So here we can see that this star's motion and this orbit precision both are in same direction. So this one is the positive precision. The second one I have taken is the Janice, Newman and Winokur spacetime, which is naked singularity spacetime. So Jane W spacetime is the solution with the scalar field charge. Now here if we take this q equal to 0 and this n equal to 1, then this spacetime will behave just like this Schwarzschild spacetime. Now here in this orbit plot, we can see that this star's motion and this orbit precision both are in opposite direction. So this one is the negative precision. So the third one is the Joshi Malafarina Narayan 1 JMN 1 spacetime, which is spherically symmetric, static and non-vacuum solution with zero radial pressure. So here we can see that this brown circle is the perihelion approach. Now this orbit, particle orbit, is approaching this perihelion approach before its 2 pi rotation. So this one is the negative precision. In the right hand side, in this figure, we can see that the star's motion and orbit precision both are in same direction, and this orbit's perihelion approach is after 2 pi rotation. So this one is the positive precision. So here we can see that the naked singularity spacetime JMN 1 spacetime gives us the negative and positive precision. The other one is the JMN 2 spacetime, which is also spherically symmetric, static and non-vacuum solution, but with isotropic fluid. So here, this black circle outside this orbit shows the position of matching radius with the exterior spacetime, which is Schwarzschild spacetime. Here also we can see that this star's motion and this orbit precision both are in opposite direction. So this one is negative precision. In the right hand side, this one, here we can see that this star's motion and orbit precision both are in same direction, anti-clockwise. So this one is the positive precision. The fifth one is the Kerr spacetime, which is the rotating solution. Here A indicates the rotation parameter. If we take this A equal to 0, then this spacetime will reduce to the Schwarzschild spacetime. This one is the potential plot for the particular value of mass, angular momentum, and energy. Now we know that if we want to know about the horizon, then putting this GRR tends to infinite. So for that, taking this delta equal to 0, we can get two equations. The first one is this R plus or minus, which is equal to M plus or minus root of M square minus A square. Now here, if we take this value of mass more than the value of the spin parameter, then we can get this black hole solution in this spacetime. And if we take this value of mass less than this rotation parameter, then we will get the solution for the naked singularity spacetime. So which we have done here. Here in the left hand side figure, we have taken this rotation parameter value less than the mass. Then here we can see that the star's motion and this orbit precision both are in same direction. We are getting the positive precision, and this black dotted orbit indicates the Schwarzschild spacetime with rotation parameter A equal to 0. In the right hand side, this blue line is for the Kerr naked singularity spacetime, and this black dotted line is for the Schwarzschild spacetime. So here we also see that this particle motion and this orbit precision both are in same direction. So this one is the positive precision. So concluding this, we have see that the Schwarzschild and Kerr both spacetime allow only the positive precision of this particle orbit. On the other hand, this JMN1, JMN2, JNW naked singularity spacetime allows the both type of precision. So now, if the orbit of S stars precedes in the opposite direction of S star's motion, which is the negative precision, one may conclude that the black hole solution Schwarzschild and Kerr are not possible around the center of our Milky Way galaxy. But if the positive precision is observed, then we can say that the black hole or a naked singularity can exist at the center of our Milky Way galaxy. So,
Thank you very much. Any questions for Vishva? Marshall, you have unmuted if you have a question.
Yeah, I mean, a positive precession is the same as a negative precession, at least at the apoapse, if you just flip the orbit over, if you think about it, right? We don't know sort of which way is which, and these are Schwarzschild type models, and so there's no rotation anyway. So really the crucial observable there will be what's happening near periapse. Are you coming into periapse before you should or after you should? And you know, I was just wondering how observable that would be. It seems like just getting the precession of the perihelion, you know, the precession of the orbit is not enough here. You need to know something about how the orbit is behaving when it's right close to the object. And presumably the most elliptical orbits will be the most sensitive. So we're thinking about fairly elliptical objects here. I know that's not quite a question, but I was just sort of thought, that was my reaction reading through, listening through this was, you know, it's not that easy because you have to look at what's happening right when you're going through perihelion or periapse.
oh,
I mean,
yes, maybe because
so would you
this
agree with
one
that,
is the
Vishva?
Hello. Hello.
Hi, we can hear you.
Maybe you are right. This one may be the crucial information to get, but this one are just theoretical models. So yeah, maybe it would be hard to get this experimental data, observational data.
Another question that I have is that, is it possible for you to obtain this kind of precession with just other baryons or even say a spike of dark matter that happens to be in the vicinity, if the potential is not purely dominated by the black hole, for example.
Oh, maybe yes.
Okay, so our remaining speakers, I believe, have not shown up, but please shout out right now if I am wrong about that. So we have time for extended discussion among any of the presentations that have been occurring in the session, or feel free to jump into a different breakout room where other talks are continuing.
Okay, let me ask a question. My name is Ranjani, and some of you might know me. I'm the digital backend person, so I'm an instrumentalist. But I'm curious to know what is it for the ngEHT? Is any of the stuff that you guys have been talking about, is any of it possible even to be detectable, even with dedicated array plus the sites we already have? So to me, that seems to be the most important question. I mean, if you tell me as an instrumentalist that, okay, this is something we can really see if we had this kind of sensitivity and this kind of angular resolution, and et cetera. But so far I haven't gotten that sense. So something that would be useful to me as a backend person, digital backend person, would be to have some sense of what would be the most feasible to look for, or in terms of exotic physics.
Well, yeah. Do you understand what drives the dynamic range of the images?
Yes.
So what dynamic range could we get?
Well, let's see. I mean, right now, I cannot tell you because we haven't made a decision on the bandwidth yet. So we could, we are shooting for a potentially 8 gigahertz bandwidth, but it could be as much as 16. I don't know. That's why I'm asking these questions. I'm curious to know. So, for example, if some of these are driven by dynamic range requirements, and something like having more higher sensitivity will help, then maybe we have to focus our attention on getting higher bandwidths. So it's possible to get higher bandwidths from receivers. It's not that difficult. It's just a question of implementation. So
is dynamic range just a matter of sensitivity of SNR? The higher the SNR, the better the dynamic range?
I mean, other than that, what else would be there?
Well, I don't know. I'm asking you. I guess the answer is then no. Instrumental stability, for example, phase calibration.
Yeah,
phase,
yeah. I mean,
you gotta avoid leakage from the photons you have into the air, which are in one area, to where they're not, which is in another area. So the leakage stuff matters.
So I'm sorry, are you talking about what kind of leakage? Are you talking about cross polarization leakage, sideband leakage?
Well, we were talking earlier about setting a limit based on the brightness at the center of the shadow versus the brightness of the rings. Mm-hmm. So that's the dynamic range I was referring to. How dark is the shadow compared to the rings? Is it? Somebody said it was a factor of dynamic range of 10 right now, or 5 or 10 down here somewhere. And maybe we could do 1,000. And I was like, well, okay, what does that mean? And it seems like if you're talking about 1,000, leakage of signal power kind of starts to matter, right? Because you need to have 1,000 to 1 reduction of any leakage. You got a fairly bright region near a fairly dark region. So and you're not really looking at photons, you're looking at phase and you're inferring brightness from that. So,
right.
I mean, you are looking at photons, but you know what I mean? You're not looking, it's not
Yes.
like you just got a CCD counting photons.
Yeah, agreed. So, I mean, that is up to the phase calibration. I mean, that is how good you can, get your phase calibration too, right? And presumably, from all the talks that I've heard today, you can get pretty decent phase calibration, and the receiver, of course, the noise performance of get more sensitivity. Of course, the noise performance of receivers is getting better. So that does help as well. But yeah, I mean, like I said, to me it seems very, how should I put it? Not very clear to me as to which of these is actually possible to do. Or in other words, one of the talks was talking about looking at a population of supermassive black holes. So that relates kind of to your question, what would be the upper limit of being able to detect one of these supermassive black holes, given that, remember the talk that we had yesterday where, I'm sorry, please correct me if I'm wrong, where it looked like the core luminosity dropped as the size of the supermassive black hole increased in size. Am I right about that? Or am I remembering it wrong? So there was a talk presented yesterday, I believe. If I'm incorrect, please correct me. So I was curious to know what was the population of supermassive black holes you would be targeting with the ngEHT. I mean, certainly M87 is somewhat of a low-hanging fruit at this point, but what would be the limits would be something that I would be very interested. So,
are you asking like for specific sources? I mean,
I'm sorry.
Are you asking for specific sources or?
No. I'm just talking about not specific sources. I'm just talking about the limits of what we can detect in terms of supermassive black holes. So the 6 billion solar mass black hole. Okay, so how massive would it have to be? How far would it have to be where we would not be able to detect it anymore? Something like that. Some very simple, questions about just let's even say distinction, as you said, the factor of brightness, as you mentioned, between the dark and between the dark portion and the bright portion, would at least have to be some reasonable number, right? So when we talk about detections, I'm assuming you want some reasonable factor of 5, factor of 3, a difference in brightness, whatever it is, whatever you guys want to use as a criteria for detection of a shadow, so to speak.
But I think a lot of that is driven not by whether or not these exotic physics or modifications to gravity or so on. It's driven by how well do we understand the astrophysics. And like that's going to be the right, that systematic error in the modeling is going to be the primary source of error in any of these. So you always want to push to better resolution, better dynamic range, better everything.
Right.
Yeah, the answer is always more.
Yeah, exactly.
Well, yes, of course.
And yeah, I mean, like in terms of an actual number, it's difficult to say because a lot of this, I mean, it's hard enough to simulate in GR, doing like full MHD simulations with all of this exotic physics. I don't think anyone's really done that.
Okay.
So one thing that would be nice, clearly, for exotic physics is, which is related to the last talk, is being able to follow and track satellites of the black hole. And in the discussion yesterday, it looked like that might not be possible for any source except for Sagittarius A star. But if you had intermediate mass black holes, or if you had other sources, and I'm being vague here because I'm not sure what they would be, but if you could do something like what's been done with the source S2 at Sagittarius A star on other black holes, that would be very interesting. And my favorite here is OJ287, which we have a pretty good idea is actually a binary. And, you know, could you detect the secondary source, for example, the secondary object, which is still a fairly large black hole, although it's a lot smaller than the main black hole, but still, you know, and, you know, what would it take to do that, and so on, you know. But you had two objects there other than one, and I would actually, I think, tell you a lot about the physics of what's going on there. But really, I think to answer these questions, you got to get into simulations. I think that's why nobody's speaking up. It's like you have to do the simulations, and if you haven't done the simulations, then you're just kind of guessing.
Well, that's okay. I'll take the guesses at this point. It's just sort of a for people like me, it's at least kind of a pointer as to, you know, where things are going, or you know, where your guess may be wrong, but at least it gives me some kind of idea. So
all right, so as I've written in the chat, we are at we're now at 17:55. It was the LOC's goal to close the rooms at this point and have the next session start in 5 minutes from now. But now would be a good time to refill your coffee cup or stretch your legs if you are so inclined. Otherwise, feel free to continue discussion.